Hello and welcome to this presentation on rotating a linked list. In this presentation, we will walk through the problem, the solution approach, and the code implementation step by step. Let's get started. Given the head of a singly linked list, our task is to rotate left the list k times. In the first example, we have a linked list with the nodes 10, 20, 30, 40, and 50. After rotating it 4 times, the output should be 50, 10, 20, 30, 40. In the second example, we rotate the list 6 times, resulting in the list 30, 40, 10, and 20. Let's look at the high-level approach for solving this problem. We begin by handling any edge cases where the linked list might be empty or no rotations are needed. Next, we calculate the length of the list, then reduce k by taking the modulo with the list's length. After making the list circular, we traverse it to find the kth node. Finally, we update the head of the list and break the circular linkage to complete the rotation. The first step in our approach is to handle edge cases. If the linked list is empty or if no rotations are needed, we can simply return the original list. If k equals 0, no rotation is necessary. Similarly, if the list is empty, we don't need to make any changes. To perform the rotations, we need to know the length of the linked list. We traverse the list and count the number of nodes. This helps us later when reducing k by taking the modulo of the list length. Once we have the length of the list, we reduce k by taking the modulo with the length. This ensures that we only perform necessary rotations, as rotating the list by its length brings it back to the original configuration. Now that we know the length of the list, we make the list circular. This allows us to easily rotate the list without worrying about boundary conditions. By linking the last node up to the head, we can rotate the list efficiently. Next, we traverse the list to find the kth node. This node will become the last node after rotation. We stop at the node just before the kth node because that will become the new tail. After finding the kth node, we update the head of the list to be the node after the kth node. We then break the circular link by setting the next pointer of the kth node to null, thus completing the rotation. Here's the complete code for rotating a linked list. We first handle edge cases, then calculate the length of the list, reduce k with modulo, make the list circular, and finally perform the rotation by updating the head and breaking the circular link. Now let's talk about the time and space complexity of our solution. The time complexity is big O of n, where n is the number of nodes in the linked list. This is because we need to traverse the entire list once to calculate its length and once more to find the kth node. The space complexity is big O of 1 as we only use a constant amount of extra space. In conclusion, we have covered the solution to the problem of rotating a linked list. The key takeaways are: handle edge cases, reduce k using modulo, convert the list to a circular one for efficient rotation, and finally update the head and break the circular linkage. Thank you for watching this presentation. Welcome to this presentation on trapping rainwater the second. Today we will explore the problem statement, approach, code implementation, and complexity analysis to understand how to efficiently solve this problem. Let's start with an introduction. In this problem, we are given a 2D elevation map represented as a grid of integers. Each cell represents the height of the cell in the map. The goal is to calculate how much rainwater can be trapped between the cells after it rains. We will go through the problem statement and its constraints, then learn an efficient approach using a priority queue, and finally analyze the complexity of our solution. Here's the problem in detail. We need to calculate the total amount of rainwater trapped after a rainfall on a 2D elevation map. The water can only be trapped between higher boundaries, and the water cannot accumulate on the grid edges. The challenge is to find an efficient way to compute the amount of water trapped while respecting the given constraints on grid dimensions and boundary conditions. The key idea behind our solution is to use a priority queue or main heap to process cells in increasing order of their heights. We begin by processing the boundary cells which form the limits for where water can be trapped. By comparing the heights of neighboring cells, we can calculate how much water can be trapped at each cell. This approach ensures we process the lowest boundary first and avoid unnecessary computations. Let's visualize the algorithm with an example. Here is a 2D grid. Initially we add all the boundary cells to the priority queue. The cells inside the grid will be processed based on their height, starting with the smallest boundary. As we process each cell, we check its neighbors and calculate the amount of trapped water based on their relative heights. Let's take a look at the code. First, we define our solution class and the trap rainwater function. We handle each edge cases where the grid dimensions are too small to trap any water. We initialize a priority queue and a visited array to track the cells we have already processed. Then we add all boundary cells to the heap. Now let's focus on the initialization part. We loop through the grid and add all boundary cells to the priority queue, marking them as visited. Boundary cells are crucial because water cannot be trapped there and they act as the initial boundaries for the algorithm. Next, we move to the main part of the algorithm. The goal is to process cells in increasing order of their heights. We extract the cell with the smallest height from the heap and check its neighbors. If a neighbor is lower than the current height, we calculate the trapped water and add that neighbor to the heap with its updated height. This slide handles the logic for processing each neighbor. For every unvisited neighbor, if its height is smaller than the current height, we calculate how much water can be trapped there. The trapped water is added to the total count and we update the neighbor's height, pushing it back into the priority queue. Now let's look at the complexity of the solution. The time complexity is big O of m times n log m times n, where m and n are the dimensions of the grid. This comes from processing each cell once and performing heap operations, which are logarithmic in nature. The space complexity is big O of m times n, since we need to store the visited array and the priority queue, both of which can hold up to m times n elements. Let's walk through an example. Here is the input grid. We begin by adding the boundary cells to the priority queue. These cells form the boundaries that determine whether water can accumulate. Next, we process the smallest height cell in the heap and calculate the trapped water for its neighbors. Continuing with our example, we repeat the process of extracting cells from the heap and calculating the trapped water. The trapped water accumulates in the valleys formed by higher cells. After processing all the cells, the total water trapped is 4. This is the final output of this grid. To summarize, we solved the trapping rainwater, the second problem, using a priority queue to process boundary cells and their neighbors in increasing order of height. This approach ensures an efficient solution with a time complexity of big O of m times n log m times n, which makes it suitable for large grids. We also discussed real-world applications such as simulating water flow and predicting floods. The key takeaways is the importance of understanding the 3D water trapping logic and optimizing the solution using a main heap. Thank you for your attention. We have covered the problem, the approach, code implementation, and the complexity analysis. If you have any questions or need further clarification, feel free to ask.